angle of reflection are the same. And you already knew that. Okay, you use it every day. And you probably use it every day for light, right? Let's say you get into your car and you adjust your rear view mirror. Are you just like randomly guessing, maybe if I just twist it around a lot, it'll be perfect? You turn it because you know which way you need to adjust to see the things you need to see. Okay, if you are trying to adjust your side view mirror, same thing. So you know how mirrors work. Okay, so this is an example of a ray diagram. Let's talk about different types of reflection. There are two different types of reflection. The first type is called specular, which is what mirrors do. Specular is the assumption that the surface is completely smooth. Okay? If the surface is completely smooth, then the light will reflect in a very predictable way. You have parallel rays coming in and parallel rays coming out, and I can form really nice, clean images because I know that every part of this mirror or this surface will reflect incoming rays in the same way. Okay? Diffuse reflection is if you have a surface that's not perfectly smooth. Okay? It's not perfectly smooth. It's rough, and therefore it still follows, each individual ray follows the law of reflection, but since the surface is like pointing in all different directions, the law of reflection makes incoming rays go kind of all over the place. Okay? So for a mirror, it has to be not only smooth, but completely reflective in the sense that it doesn't absorb any light. Okay? So the wall, for example, is not completely reflective, and it's diffuse because it's not smooth enough and it absorbs some colors of light. Okay? But the diffuse part of this, the diffuse reflection, is that it's not smooth. Is there a question that you're thinking about right now? Something you want to clarify? How do we define smooth? What is smooth? What does that mean? Your table is smooth-ish, right? Is it a mirror?
Somewhere.
Kind of, right? It's sort of a mirror. So is it smooth or not smooth? Is it smooth enough? I don't know. But there is one thing that helps you define smooth. Okay, and it sort of has to do with this thing here. What is this a picture of?
Oh, the array.
The Very Large Array, which you learned about yesterday. It is in New Mexico. Has anyone ever been to the Very Large Array?
No.
It's incredible. It's
large.
This is unbelievable. This is the coolest telescope in the entire world. There are 27 radio telescopes, and each one of them is like 10 stories tall, 25 meters wide.
Wow.
And they form this Y shape, and basically it acts as if it's a giant telescope with the diameter of that thing. And you can change the size of it because each one of them is on railroad tracks. So if you want to make the entire thing spread out to increase your resolution, you can make each arm of this like 10 kilometers long.
Wow.
It's crazy. So all you do is put this on the railroad track, move it along down.
Wait, so
to
each one of those is an individual telescope?
Yes, each one is an individual telescope, but they use it as an array, a combination.
How do they put it on the railroad? Aren't they heavy?
Yeah, they're incredibly heavy, but this is also a railroad, so it goes out and then it can turn and then it comes along.
That's be a lot
Actually on skateboard wheels.
Yeah, so these were built, this was built in like 1970. All the technology is the same. The electronics, they've just updated in the last like 2 years, but they were using the same electronics from, 40 years ago. Anyway, so the reason I bring this up is because when we think about like a telescope, right, or the mirror lab, that's at the U of A, they polish those mirrors for like days and weeks and months so that they're completely perfectly smooth. These, birds poop on them, hail, snow, people walk on them.
Nice.
What's the difference?
Well, they're going to get grubby.
It's true, they're going to get grubby, but why is that okay?
Because they're so big.
Because they're image.
interesting point. That's not the case. The reason is because radio waves have a longer wavelength, and so they're less susceptible to being diverted by those tiny little bumps in it. Okay, so the amount of smoothness that's required is proportional to the, or inversely proportional to the wavelength of the incoming rays that you're trying to focus.
Do they try and still keep them pretty clean though? Like, do they polish them and stuff?
No. They let people walk in them. So for size reference, this is a person right here.
Not a heavy.
It's cool. I did it once. You climb up all these ladders and stuff. There's like a control room in here on all the electronics, and then you just climb up and it's like coming out of like an attic onto the roof. Like you just open like a hatch and you crawl out, and then you're in the dish.
That's safe.
hot.
Super steep at the edges, and it's kind of terrifying. Yeah, no, it's not that safe, but
Is it hot?
Like a soccer.
Wait, They permit you to
I
do
went there in the summer, and it wasn't that hot.
Do they let you play soccer? That'd be so cool.
No.
Think about it.
They
You just like
train
kick the
them,
ball and
correct?
goes all the way around and comes back.
You wouldn't. It's actually, well, I don't know. I'm not really that afraid of heights, but I was like a little bit, I didn't like it that much. Yeah, definitely focusing the light on it. So whether it's diffuse or specular reflection depends on a lot of things. One of them is the wavelength of the light, right? If you're trying to focus radio waves, it's super easy. These things have dents in them. They're made out of like, I don't know, sheet metal or something, right? Whereas the mirrors at the U of A, or even like a mirror that you have in your house, has to be really, really nicely polished and smooth. And that's the difference. And so when we talk about visible light, in order for something to have this specular reflection, it has to be, there have to be like no imperfections in it. But this is the difference, I guess. Okay, so we use ray diagrams, and you're going to see a lot of ray diagrams in the coming days, to find the location and the size of an image qualitatively, meaning without actual numbers. And we're going to start with plane mirrors. Plane means flat. Okay, so I know that the spoons are exciting and interesting, but we're going to talk about flat mirrors at first. So why don't you take a flat mirror and just look at it for a second. There are two realms when we talk about mirrors. The first area is in front of the mirror, where you are. Like this is you and this is the mirror. That's where you are. You're in the real world. Okay, and then there's the like in the mirror land. Okay, it's behind the mirror, as we say. But it's not actually a place, right? You can't be in the mirror.
Harry Osborn did it.
Thank you very much.
Harry Osborn.
So I'm going to refer to that as imagination land. Okay? Behind the mirror, we have imagination land.
There's Terrence there, yeah.
I had a nice little, oh, hold on, let's start over. Okay. So imagination land is not really what physicists call the other side of the mirror. They just call it behind the mirror. But I like to think about it as imaginary world or imagination land because it's not real, right? There's nothing there, but sometimes it seems like there is. For example, when you look into a flat mirror, it seems like, it literally looks like you're on the other side. Does it not? Okay. That's why it's so creepy because, first of all, you fully understand that you're not over there. There's not another you on the other side.
Vampires are you sure?
But
That's what cats do.
your pets don't get it, right? That's why, because it looks like
I had a
it's
dog
on
who
the
died.
other side.
So,
Okay.
My dog likes it.
So to figure out why it looks like that, we draw a ray diagram. And this is a source. This is a source of light. Think about it as like a light bulb. Okay. You have a light bulb, and a light bulb emits light in all directions. Okay, it doesn't just emit like a ray here and a ray there and a ray there. It emits light in every possible direction. Okay? But we don't need to draw every infinite ray that comes out of here and what it does to figure out what's going on. If we are selective, we can choose a couple of important rays and just draw those. So I think I picked like 4. Yeah, 4. But those are not the only 4 rays that are being emitted from whatever this source is. Okay, or reflected from whatever this source is. But those are 4 rays, and they've all just hit the mirror. And because light travels in a straight line until it hits something, they've hit something, and now they're going to reflect. And each individual ray is going to reflect according to the law of reflection. And for each one of these, I'm going to draw a normal line. Okay, and plus another one just for good measure, I guess. But I drew a normal line here where it hits the mirror, here where it hits the mirror, here where it hits the mirror, and here where it hits the mirror. Because it's for reference. It's to help me to draw a line that's the same angle of reflection as incidence. So then, I draw in the reflected rays. Okay? This top ray, this angle of incidence, and this angle of reflection are the same. This angle of incidence and this angle of reflection are the same. This angle and this angle are the same, and this angle and this angle are the same. What it looks like from this, it looks like all those rays that are reflected are going in random directions. They're going away from each other. These are never going to come together, converge, and create a nice image. So in order for an image like this to be formed in a plane or a flat mirror, something else has to happen. Something else has to happen.
Absorption.
Kind of. The light has to be interpreted, I suppose, by something, or it has to be redirected or refocused by something else. For example, your eye. Okay? Your eye is a light collector, and let's say it collects all of these rays. Let's say it collects all of these rays. When it collects all of the rays, what does it do with them? Processes them in a way that is very simple and still very complex. Okay, the mechanism that your eye uses to focus the light is very simple, but then your brain interprets it, okay, in an unconscious kind of way. So your brain makes the assumption, because that's true for most things in the whole universe, that light that's coming to your eye has been traveling in a straight line for quite some time. It assumes that the light has been traveling in a straight line from the source of the light. So it thinks that this ray came from back there, and this ray came from back there, and this ray came from back there, and that ray came from back there. Because it traces it back until everything comes to a point. Okay? It traces it back and imagines or creates an image on the other side of the mirror. It's an interpretation. Without something else to interpret or take these rays and do something with them, they're just going to go in all directions, and no image will be formed. If your eye takes these rays in, it knows what direction they came from, and it traces back to the origin of those rays. Right? Think back to your pets. They don't have that added knowledge of, oh, there's a mirror in front of me. Sometimes it happens to you too. Don't pretend it doesn't. Right? Like if you're in like a restaurant and you think the restaurant's really huge, but it turns out it's just a giant mirror. Has that ever happened to you before?
Yeah.
Yeah, or
You're in the bathroom and you see another person, it's just you.
yeah, exactly.
I've been in the bathroom where the mirror's like right across eye level. Right there, so creepy.
Yeah, so there have been times in all of our lives when a mirror has scared us because we didn't know it was there. And as soon as you know there's a mirror there, then you can process further the information that you're getting. But your eye and the part of your brain that just like instantly makes sense of what you're looking at says that the image is behind the mirror. Okay, and it all has to do with this law of reflection and the ray tracing back into imagination land. That's why you see yourself. Your image is on the other side of the mirror. Okay? Okay, let's do something a little bit more interesting, like an object that is extended, that has shape to it. We use arrows a lot because arrows have a clear top and a clear bottom. Okay, so you can tell if it's upside down or right side up or whatever. And if we have something like this could be a person or anything that has like a top to it. We can imagine that every point on this is giving off rays in every direction. Okay, whether it's emitting rays or it's reflecting rays, it doesn't matter. We see things not because we're emitting light, usually, right? If you're looking directly at a light bulb, yes. But if you're looking at anything in this room, besides this, well, even that, besides the light bulb, then it's not emitting light, it's reflecting light. And that's why you see it. Okay? But it's not reflecting light specularly, like we talked about before. It's diffusely reflecting light in all directions. That's why this seems like there are rays going in every which way. Okay? But once again, it doesn't help us to draw every infinite ray coming from this point, and every infinite ray coming from this point, and every infinite ray coming from this point, and this point, and this point. It helps us to find the location of the image of the top of this arrow. And in doing so, we can figure out the location of the rest of the image. So if I draw a couple of rays, there's one, and I draw its reflection, whoops, sorry, and there's all the random ones. I got excited with my PowerPoint here. Then I can draw its reflection. Okay, I notice I drew in the normal automatically. The normal line doesn't have to continue as long as I drew it. Sometimes if you have lots of them, you might want to make them shorter. But that's one ray. That one ray doesn't give me enough information to figure out the location of the image yet. But if I draw another one, and then I draw the normal, this one has a different angle of incidence, so it's going to have a different angle of reflection, just like before. So you've got angle of incidence, angle of reflection, angle of incidence, and angle of reflection. Neither one of these two rays is going to converge or cross one another in the real world, in front of the mirror. The only way they can cross one another or converge is if you have your eye trace them back behind the mirror. So your eye says, I know one thing about light, and then it travels in a straight line. So this ray must have come from back there, this ray must have come from back there. Therefore, the top of this arrow, the image appears where those two rays converge. And so the image of the arrow is on the other side of the mirror. In the same way that we found the image of the dot on the other side of the mirror. Okay, but the difference is I could do that again with the bottom of the arrow and find the location of the image at the bottom of the arrow, and then I have an entire extended object.
Wow.
This is a flat mirror though. So in a flat mirror, there are a couple of things that are really nice and easy to remember. One, the image is the same size as the object. Okay, you know that to be true. Two, the distance between the object and the mirror is the same as the distance between the image and the mirror. Okay, so if I'm standing 1 foot away from a mirror, my image is 1 foot behind the mirror. Okay. And when we're talking about all of these properties of these objects and these images, we use some variables, and here they are. There are 4 of them. The first one is HO, height of the object. HO is the height of the object, the size of the thing that you're making an image of. HI is the height of the image. So in the case of a plane mirror, HO equals HI. P is the distance from the object to the mirror, and Q is the distance from the mirror to the image. And in this case, for a plane mirror, P is equal to Q. That's the only time. If your mirror is not a flat mirror, those things are not always true. That's why we use flat mirrors, because it's supposed to show you actually what you look like, what size you are without any sort of magnification or minimization, I guess. So I want to show you why when you look in the mirror, your face appears to be a mirror image of itself, right? Why is it that when you look in the mirror, you don't see what someone sees when they look at you? Your left eye appears to be your right eye, right? So let's talk about why that is. And it has to do with, So this makes hold on. So when we talk about images, no matter what, we always ask the following 4 questions. Is it real or virtual? Is it inverted or upright? Smaller or larger or the same? Closer or farther or the same? Okay, so let's talk about real or virtual. Real or virtual means which side of the mirror does the image form on? In the real world or in imagination land? If the image forms in imagination land, then it's a virtual image. Another way to think about it is if the rays, the reflected rays, don't actually physically cross one another, if it requires your eye or something else to take in those rays and interpret them, trace them behind the mirror, then it's a virtual image. Okay, so this image is virtual. Was the image inverted, meaning upside down, or upright, right side up?
Upright.
The image was upright. Smaller or larger are the same? Same. Closer or farther are the same? Same. Okay. Okay, now let's talk about your face. I've color-coded these 2 eyes different colors so that you have a sense of where the light is coming from and what it's doing. We're going to pretend that we're talking about what your brown eye is seeing. Okay? So right now, we're talking about this as the light collector. And we're going to talk about this right now as the light emitter, okay, or reflector. The light is going to come from here, this eye, and it's going to go into this eye. Okay? So this is you looking in the mirror. So there's, let's say, a blue ray that comes from your eye, this one, and it hits the mirror. And that ray reflects into the other eye. Okay, so you see that. And let's say there's another blue ray that hits at a different angle and then reflects into your eye again. I've drawn the 2 normals. Okay, I've drawn the angle of incidence and the angle of reflection the same. This is the eye that's just emitting light for the moment. Okay, you can imagine that it's not a real eye. Okay, it's not collecting any light for you to interpret just yet. And this is the eye that's collecting the light. So this is the one that's saying, okay, I've just received these 2 rays, plus all the other ones that I didn't draw. And I know that light travels in a straight line, so these 2 rays must be traced back behind the mirror. So it looks to me like the origin of these 2 rays is over there. Okay? Okay. So then, let's pretend that this is also the light emitter and collector. So I have a ray that comes from this eye and then reflects back into that eye. And then let's say I have another one. And they're both traced behind the mirror to converge in imagination land. So what this eye is seeing, and you can do it backwards too, right? You could just switch all of the arrows and then everything would be as it is for this one. But what this eye is seeing is that the blue eye is over there and that the brown eye is right in front of it. Or vice versa, this one will see the blue eye over there, the blue eye in front of it and the brown eye over there. Okay, that's why it appears to you that you're a flipped image of yourself. Does that make sense? Okay. Okay. Let's talk about more than one mirror for a second. This is two mirrors, and they're at right angles to each other, perpendicular to each other. And then I have some sort of source of light that I've placed kind of randomly there. And that source of light emits rays in all directions, right? But there are only certain ones that I'm going to draw because I only need a certain number of rays for this to work out. If I'm standing here and I'm looking in these two mirrors, one thing I could do is pretend that this one's not here, right? If that's true, where should my image form if I'm looking into this mirror?
On the left side.
On this side. And how far away from the mirror should it be?
Same distance.
Same distance.
Exact same distance and directly behind, right? Okay. How about here? If I forget this one, then this one should form
Underneath.
exact same distance and directly behind. Okay. And those two images should form still. It's not like having two mirrors makes those images not exist. But what happens is there's also a third image that's formed in this case. And I'm going to show you how and why that's done. So if I draw some random rays, okay, and notice I've already drawn in the normal lines that exist at those points. I can draw in the reflection of each one. So there's the reflection of the top one. There's the reflection of the next one. There's the reflection of the next one. And there's the reflection of the next one. Now I've sort of color-coded these for you. The red ones reflect and then go away to something else. Okay? The blue ones reflect in such a way that they're going to do what? Reflect again. Okay, but let's just pretend for 1 second that that's not going to happen. And we're just going to trace those red rays. No, sorry, we're going to trace all of them back behind the mirror. So trace that one back and that one back. And look, this ray and this ray do form an image directly behind this mirror. Okay? That ray and that ray do form an image directly behind that mirror. But then we have to consider what happens next. Yes, this ray is something that I can trace back behind the mirror, but it also is going to bounce again. And this ray also is going to bounce again. So I need to draw those. That one, the purple one on the bottom right there, is the reflected ray of the blue one that went down into the right. Up here now, there's the other reflected ray. And I can trace those back behind the mirror, and I can come up with a third location of an image. So there's one image, there's two images, and there's the third image. So try it. Take two mirrors at your table, make them perpendicular to one another, and see if you can find the location of those three images of yourself.
I see him. That's great.
I already know.
I obviously know, but
We'll not find the location, but see if you can find all
Experimented with mirrors before.
four.
Yeah.
Oh, I see. 4 years.
I want to know.
Don't touch it.
Does it help if you put an object instead of your face?
To me it is.
Okay, yeah. There you go, okay, yeah.
So frustrating.
Take a picture of it. Somehow. I don't know.
The camera on your eye, literally.
But then you have to be careful not to make it reflect. Are we finally going to be able to use that big mirror now?
I've never used it before, so I'm a little hesitant. Yeah, I'm gonna like set myself on fire.
No. Let me get it.
So another way to think about this is that each mirror individually makes an image, and then this actually makes an image of the image. It is pretty weird, but if you imagine now this ray coming from here and reflecting, if I take an image of, so this is the image of this in this mirror. If I now draw rays, assuming this is the object, making this the object, taking an image in this mirror, then it traces back to here. If I make an image of this image, it traces back to the same place.
So it should be in the same spot.
Yeah, so the image of this image in this mirror is here, and the image of this image in this mirror is here also.
Wow.
So it's an image of an image, is a good way to think about it. Yeah. Now let's do one more interesting thing, and that is to talk about
I don't even know what my notes are.
plane mirrors and seeing all of yourself. When you look in the mirror, let's say you have a mirror that's that size, here's the mirror, and these are the two edges of the mirror. If you want to see more of yourself, what do?
Step away.
You step in.
You step away.
What? You step
Yeah.
in. You go into the mirror.
No, you step away.
Imagination land. Yeah.
You become a deity.
You become a deity.
If you move away from the mirror, how much more of yourself do you see? Well, what determines how much of yourself you see is dependent upon the edge of the mirror and where your eye is, right? My eye can only see rays at the very extreme that have come from this point here, right? And this angle is very specific. So this is if my eye is right there, this is the lowest part of my body that I can see in this mirror. Okay, if I wanted to see my feet, the ray from my foot would go here and then miss my eye. Okay, so that's the part of my body that I can see. And then here's the top part. I can definitely see the top of my head, right? Because I could see even more than that if I wanted. Oh, sorry, no, I couldn't. But that's the extent of what I can see. Now, if I move the mirror back to here, what I can see is exactly the same. It does make sense. But I still didn't believe it when somebody told me, I don't know, 10 years ago, more than that probably. And I was like, I've done it before. I bet you're all thinking that. I've done it before. I was like, I have definitely done that before. But you haven't. I guarantee. Go home and try it. Try it now.
I am.
If you, try it now. Or go home and try it. And it'll blow your mind. Because you thought you were doing it, but you weren't. It's crazy, right? But if you draw the ray diagram to see what the extent of what you can see is, it's always going to be the same amount of you.
How do we see our
Huh? Bigger mirror or tilt it.
Shit.
Okay.
He thought he was gonna prove it.
Okay, so I have some homework for you, and also please turn in the homework that